Welcome to this lesson. Before we begin, this is Psalm 33, verse 18 and 19. But the eyes of the Lord are on those who fear him, on those whose hope is in his unfailing love, to deliver them from death and keep them alive in famine. If you'd like to take a moment of silence now, if you don't believe in God, or if you'd like to take a moment and pray, then you can do that. So our lesson today is on what's called binomial experiments. So the first part of the notes, I'm going to explain what a binomial experiment is, and then I'm going to relate it to something you've seen before, and then we'll do some examples, and then we'll be all done. Binomial experiment exists if these conditions occur. First, there have to be exactly two possible outcomes for each trial. So we call that binary. Binary means there are two possibilities. We usually talk in terms of success versus failure. So if you think about rolling a die, we'll say it has 6 sides, 6-sided die, it's fair die. Success and failure would be probability of getting a 1 on the die. Success would be getting a 1. Failure would be not getting a 1. So it has success and failure. Number 2, trials are independent. So I for independent. Dice rolling are independent events. So the probabilities remain the same regardless of how many times you roll the die. Getting a 1 is always 1 out of 6 on a die. Number 3, there are a fixed number of trials. That means you'll be told you roll a die 20 times. 20 would be your fixed number. So it's 20. So you're told 20, fixed number of trials. And then the probabilities of success for each trial are the same. So S for the same success. So probability of getting a 1 is always 1/6 on a die. It doesn't change. It's the same. So the letters that I use are BINS, B-I-N-S, which is kind of short for binomial experiment, B-I-N-S. And it just helps me remember what the 4 things are. Binary, independent, number of trials is fixed, and then S is success. Probability of success is the same. Okay, so determine if the following qualifies as a binomial experiment. You roll a fair die 10 times, let X be the number of 6s. First for B, binary, you have success and failure. Success is getting a 6. Success is a 6. Failure is not a 6. I is independent. Are the trials independent? And you would say yes. Die rolling are independent events, or is independent. N, are there a fixed number of trials? Well, you're told you roll the die 10 times, so N is 10. And the probability of success for getting a 6 is always the same. Probability of success is 1/6. It's always the same. So you would say yes. This qualifies as a binomial experiment, which I haven't told you how to do a binomial experiment yet, but this qualifies for one. Let's see, letter B. I'll tell you right now, B and C, there's a problem with B, and there's a problem with C. So B, shoot a basketball 20 times from various distances on the court. Let Y be the number of shots made. Now this is binary. Success would be making a shot. Failure is missing a shot. So that's okay. It has a fixed number of trials, 20. The problem is the I and the S. So this right here, when you're shooting basketball, your probability of success changes. If you're right under the basketball hoop, you'll probably make a lot more than if you're way back at the half court and shooting like way far back. So the probability of success changes. Probability of success changes. It's not the same every time. Changes based on distance. And you could also argue that the independent condition isn't always, that the events aren't independent, because maybe if you've been shooting for an hour and you're tired, and maybe you're missing shots because you've been shooting for so long. So now it's dependent on your energy level, which you didn't really have with rolling dice. So there are 2 problems with this. So it's a no. This is also a no. Observe the next 100 cars that go by and let C, the event, be the color. The problem is this isn't binary. Or to say it a different way, what's success? That's a question mark. So what's success? You're just looking for a general color? Like, how do you know if you succeed? All cars have color, I guess, unless it's white, if you count white as a color, absence of color or something. So that's a problem. You'd say no, it doesn't work for that. Okay, the next part, try to illustrate a connection between binomial expansions, which help us to solve binomial experiments. So let's imagine that you want to know what's the probability of getting 4 out of 5 questions right on a test, and you guessed at every question. You need to take into consideration all the different combinations. You could get the first question right, and the second, and the third, and the fourth. These are all right, R for right. You can get the last one wrong. Another combination would be you get the fourth one wrong. You can get the third one wrong. So I'm still getting 4 out of 5, but it depends which one you miss. You can get the second one wrong, or you can get the first one wrong. So notice there are 5 ways to get 4 out of 5. 4 out of 5 right. 5 ways. I'd like to relate that to something we did in the last chapter, which is a binomial expansion for r plus w to the 5th. So if you think back in the last chapter, if you wanted to do r plus w to the 5th, first we need Pascal's triangle, which the 4th row are these numbers. The 5th row are these numbers. So you want the 5th row. And you use these numbers. So you have 1, 5, 10, 10, 5, 1. And you have r. You have w. And you have r to the 5th, r to the 4th, r to the 3rd, r squared, r to the first, 0. W, and then you go ascend on the exponents. So you have something like this. This is in the last chapter. And what I want you to notice, well, let me rewrite it on this page. What I want you to notice is you have r to the 5th plus 5, r to the 4th w, plus 10 r to the 3rd w squared, plus 10 r squared w cubed, plus 5 r w to the 4th, plus w to the 5th. What I want you to notice is there's a relationship between this binomial expansion, expanding this binomial, and this probability question, counting question. Notice we had 5 ways to get 4 right and 1 wrong. That's right here. So this is r is number right, is 4 right. W is the number wrong. And 5 is the number of ways you can get 4 right, 1 wrong. So if the question was, how many ways can you get 3 right and 2 wrong? 3 right and 2 wrong would be this one. There are 10 ways that you can get 3 right and 2 wrong. And we could list them all out, but there's going to be 10 of them. How many ways can you get them all wrong? Well, that would be, there's one way to get them all wrong. You get them all wrong. So this right here, this expansion, is known as the binomial theorem, and we can use it to answer probability questions. So here's the binomial theorem. You're going to be looking for 4 variables, n, r, p, 1 minus p. N is the number of trials, r is the number of successes, p is the probability of success, 1 minus p is probability of failure. So let's say we have a 5-question multiple choice test. We have options A, B, C, D on our multiple choice test. Each question, multiple choice, A through D. N is the number of trials, or in this case, the number of questions, 5. R is the number we want to get right. So let's say, like the previous problem, it's 4 out of 5. What's the probability of getting exactly 4 out of 5 questions right? So we do a 4. What's the probability of success? Well, if you have 4, A, B, C, D, there's only one of them that's right. So it'd be 1 out of 4. And what's the probability of failure? Well, if there's 1 out of 4 ways to succeed, the leftovers, 3 out of 4 ways to fail. And what we do with this, we use what's called the binomial theorem, which I like to write like this. You can see it also this way on the left. It looks really complicated, but actually using it's not as complicated as it looks. You would have 5 questions. You're choosing 4 to get right. 5 choose 4. You multiply by the probability of success, 1/4. Raise to the exponent how many successes you want. You want 4 successes. And then probability of failure is this 1 minus p part in here. Raised to the difference between the two. So if you have 5 questions and you succeed in 4 ways, then you have 1 question that you fail at getting it correct. So 1.5 chance. So n equals 4. R is the number of successes, which is this number, 4. Your probability of success is your batting average. How likely are you to, I don't know why I put a parenthesis there. There we go. How likely you are to get a hit. 1 minus p would be 100% minus that batting average, which is 0.685. So your probability of going 4 for 4, getting 4 hits and 4 at-bats, would be 4 choose 4. 0.315 to the 4th. That's how many times you want to succeed. And then how many times do you want to fail? Well, if you have 4 at-bats and you get 4 hits, you haven't failed. You don't fail at all. So it would be to the 0. And we could type that on our calculator. Do you think the probability is higher for 0 for 4 compared to 4 for 4? Well, 0 for 4 means you go to the plate 4 times and you never get a hit. You always get out. So n is still 4. R is now 0. P is your batting average. 1 minus p is your probability of failure. So you'd have 4 choose 0. 0.315 to 0. 0.685. And to the 4. This is to the 4 because you don't succeed at all, 0, and you fail 4 times. Fail meaning you get out, you don't get a hit. And we could do that on our calculator. 22% chance that they would go 0 for 4 rather than 4 for 4. What do you think is more likely, 1 for 4, 2 for 4, or 3 for 4? Well, you could think if the batting average is this, 1 for 4, so if we compare, 1 for 4 is this batting average, 2 for 4 is this batting average, and 3 for 4 is this batting average, which would be a really good batting average. Which one of these is closest to our average, our batting average? Well, the closest one is 1/4. So we would say 1/4 is the most likely because it's closest to his actual batting average. So you would have 4 at-bats, choose 1, batting average. How many times do you succeed? Unfortunately, just once. And how many times do you fail? 3 times. So the most likely is this.